Let us do some example problems on Bronsted-Lowry acid-base theory and conjugate acid-base pairs. Identify each of the species in the following equation as a Bronsted-Lowry acid or a Bronsted-Lowry base. So the given equation is sulfuric acid reacts with ammonia to form HSO4 minus ion and NH4 plus ammonium ion. And we are supposed to identify Bronsted-Lowry acid and Bronsted-Lowry base. By definition, a substance that donates a proton or H plus ion is called as Bronsted-Lowry acid, and a substance that accepts a proton is called as Bronsted-Lowry base. Now, if we look at the equation, the sulfuric acid H2SO4 loses a proton and becomes HSO4 minus ion. So, the sulfuric acid which loses a proton is Bronsted-Lowry acid, and the HSO4 minus ion formed is its conjugate base. Similarly, ammonia gains a proton from H2SO4 and becomes ammonium ion, that is NH4 plus ion. So, the ammonia molecule which accepts a proton is Bronsted-Lowry base, and the ammonium ion is called as its conjugate acid. Let us do one more example. HCO3 minus ion reacts with hydrochloric acid to form Cl minus ion and H2CO3. In this equation, HCO3 minus ion accepts a proton from HCl and becomes H2CO3. Therefore, HCO3 minus ion is Bronsted-Lowry base and H2CO3 is its conjugate acid. HCl, on the other hand, loses a proton to HCO3 minus ion and becomes Cl minus. Therefore, HCl is Bronsted-Lowry acid and Cl minus is its conjugate base. Next example, which of the following are conjugate acid-base pairs? Part 1, H2O, OH minus ion. By definition, conjugate acid-base pairs differ only by one proton. In this case, H2O and OH minus ion, they differ only by one proton. Meaning, if we take H2O and remove a proton, we get OH minus ion, and we take OH minus ion and add a proton to it, we get H2O. Therefore, we can say that H2O and OH minus ion are conjugate acid-base pairs. Let us move on to the next part, NO3 minus ion and HNO2. If we look at these two species, they definitely differ by one proton, but they also differ by one oxygen. In other words, if we take the nitrate ion and add a proton, we don't get HNO2, and similarly, if we take HNO2 and remove a proton, we do not get NO3 minus. Therefore, they are not conjugate acid-base pairs. Next, H3PO4 and HPO4 2 minus. These two species differ by more than one proton. Therefore, they are not conjugate acid-base pairs. One last problem on conjugate acid-base pairs. What is the conjugate acid of HSO4 minus ion. We need to find out the conjugate acid of HSO4 minus ion, which means the HSO4 minus ion is acting as a base. And we know that a Bronsted-Lowry base gains a proton to form its conjugate acid. So let us add a proton to HSO4 minus ion, which will give H2SO4. This is the conjugate acid of HSO4 minus ion. Next, what is the conjugate base of HSO4 minus ion? Again, we need to find out the conjugate base of the given ion, which means the HSO4 minus ion here acts as an acid. And we know that a Bronsted-Lowry acid loses a proton to form its conjugate base. So let us remove a proton from the given ion. If we remove a proton from HSO4 minus ion, we get SO4 2 minus ion. And the SO4 2 minus ion is the conjugate base of HSO4 minus ion. The HSO4 minus ion can both gain a proton or lose a proton. That is, it can act as Bronsted-Lowry acid and base. These type of species are called as amphoteric substances.